Alright, so basically we're going to be looking at the derivatives of the inverse trig functions with respect to the appropriate variable. So essentially, we are going to be following the chain rule for basically all of these, because they're not just going to say, oh, tell me what the derivative of arc cosecant is. Like, they're not going to just tell you to do that. Like, they're going to give you some, like, arc cosecant of x to the fifth or something like that. So we'll pretty much always be using the chain rule here. But anyways, so let's start out with 2. So y is equal to the arc cosine of 1 over x. And I would say you're probably going to want to keep your list handy so that you can look at it. Yes, obviously these are for the individual ones. You just have to remember to apply the chain rule, but it'll be easier if you have it kind of close by. So cosecant, goodness gracious, cosine is minus 1 over the square root of, it's 1 minus x squared. So basically where we see that x, we're going to put the 1 over x for this particular one. So 1 minus 1 over x squared. And then we need to also take the derivative of the 1 over x piece. So we need to do the derivative of 1 over x. So what would that derivative be? Or you can think about it as x to the negative 1. So basically that's going to come out here, so negative times negative, well, 1 over x squared trying to check here because they're so this becomes positive, so you get 1 over x squared times the square root of 1 minus, well, here I'm just going to do this, 1 over x squared. I think they have a typo here. Your book says we're taking the arc cosine, right? Okay. Then this would be true for this problem. The answer that the book has is 1 over the absolute value of x times the square root of x squared minus 1, which would be for cosecant, I think. Let me check it and verify it, but I don't see any way in which that's the case, right? Like, you don't see anything else that can be done in here or pulled out or anything that's going to get rid of an x squared outside and do something on the inside? Okay, that's what I thought, but sometimes I miss something, so I was like, let's check. Oh. Okay, so basically you can get farther down by pulling stuff out, basically making a common denominator in here, and such, but as far as I'm concerned, if you get to here, just leave it. You don't need to do all the extra stuff that's going to cancel that stuff out. Yeah, just leave it there. Because I was like, that looks like the one for cosecant. That does not look like the one for cosine. I guess if you manipulate stuff enough, it gets there, but I just don't see a point in doing all the extra work. You don't need to. Alright, so 4 is the arc sine of 1 minus t. So what is my derivative of arc cosine? Or sorry, arc sine. One over, so 1 minus, and then where we have x, we'll put in 1 minus t squared, and then what? The whole thing. And then because of the chain rule, what else do I need to have? Yeah, so I'm just going to go ahead and throw the negative sign out front here. So then how would I simplify this stuff inside? Yeah, well, it will in a sense. It'll just allow us to cancel the ones away. So basically you'll have 1 minus 1 plus 2t minus t squared, I think. Trying to do this all in one step. Yes, but I went ahead and did this negative sign through it. But yes, you are correct. That's why I said I was like, wait a second, I'm trying to put all the pieces through at the same time just to save some space. So then basically just the 1's cancel, so you're left with negative 1 over the square root of 2t minus t squared. And that's all you have to do for that one. Alright, so we're not actually going to do 6, but if you just look at it, what does it look like you would have to do there? Or what do we have going on there? Yeah. So we're not going to do that one, but just so you see what you would have to do. There's that one. With 8, trying to see what the answer is. I think, maybe, no, never mind, it doesn't work that way. I was going to say, I think you can move the negative up, but I don't think you can do that with the trig functions. I think it has to stay. I don't think, you know how like you can like flip it to the top with like an exponent? I don't think you can do that with trig functions based on what I'm seeing here. So basically you'd have to treat that like a quotient rule in a sense. Yes. Yeah, you could do that with that one. Do you want to see that one or? Okay. Alright, so we have y is equal to 1 over the arc sine of 2x, which you've already said is the cosecant, wait. Yes, cosecant? Yeah. I always have to think about it. I'm like, wait a second. Because it's like the cos that go together, like the cos go with whatever they go with. So everybody's like, sine and cosine go together. I'm like, wait, no, they don't. Seems like they should, but they don't. So, alright. So then what would we have here based on that? Hold on a second. You said you had negative 1 over 2x times the square root of 2x squared minus 1? Okay. And what else? So I have negative 2 over 2x times the square root of 4x squared minus 1. This answer is still really weird. Because that would be done, right? Like, there's nothing else I can do to this radical. Do you really want to know? Negative 2 over the arcsine of 2x squared times the square root of 1 minus 4x squared. So 1 second. Gonna have to give it a second. Because even if you left it as sine, it would be like flipped. What? Okay, so they take they say that the sine of 2x inverse, because that would be moving it to the top, is u to the negative 1. So then they say take the derivative of this, which would give you minus u to the negative 2 du. And then they're saying to use that and plug it in. So basically that you get u, the derivative of u, so you have negative sine to the negative 1 of tx to the negative 2 times 2 over 1 minus 4x squared, all that in square root. But the thing is, this is the same thing, so I would just go with that. Like, those are identical, so I'm not sure. And then they are like, rationalize the denominator. I'm like, no. How about not? Somebody else did it a really weird way. I like our method better. It just logically makes more sense to switch it to cosec it because you can. And then you don't end up with all this crazy stuff down here. I don't know. I would just not worry about that stuff. I'm not going to give you any of these that are like really hard to do. The ones like 2, 4, something like 5 wouldn't be bad either. Like it's just 3 over t cubed or t squared. Something like that wouldn't be bad. Let's try, just to get a different one, since we already did a sine one, let's do 12. That one's going to be a tangent one. So this one is finding the velocity, so basically at the point, so we just need the first derivative. And this is not something where I would have you give me acceleration and other stuff as well, because the second and third derivative would just get really crazy. So there's really no need for that. So we have x of t is equal to the arctangent of t squared, and t is equal to 1. So I need the derivative of arctangent. So what would I have then for that? Yeah. 1 over 1 plus t to the 4th, and then what else? Times 2t. I was looking at the wrong problem, and I was like, they have a square root. Something's wrong. So then this is 2t over 1 plus t to the 4th. So then I just plug in 1 for t, so I end up with 2 over 2, which is just 1, so it would just be 1 for the velocity of that one. So those aren't too bad when you have something like that. Let's see. Trying to think of which ones we already did, trying to get a variety. So we did a cosecant, a cosine, a sine, and a tangent. Let's do secant, so let's do 14. So y is equal to the arcsecant of 5s. And so then what does this give us here? That, okay. So then, oh, and then what else? Did you already say that part? I don't remember. Times 5. So 5's cancel. And so then you would get 1 over s times the square root of 25s squared minus 1. Alright, let's see. How about a cotangent one? Let's look at 18. So y is equal to the arc cotangent of the square root of t. So what do I have here then? And then times what? One half t to the negative 1/2. So on the top, I just still have negative 1 over, let's see, we're multiplying here, so 1 plus t times 2 square root of t. And that can be written in whatever order, but that's fine to just leave it like that if you want. You can move the 2 square root of t out front if you are so inclined. Alright, then, how do you feel about those so far? Yeah, I mean, if I give you the really hard ones, then yeah, they're going to be a little confusing, but, so I guess let's just do one of these tangent one, or one of these where you're finding the equation of the tangent at the point and go from there. Let's see. Let's do 26. It's a little harder. 24 is like literally just, yeah, the formula. So y is equal to the arctangent of x squared, and x is equal to 1. So you have 2x over 1 plus x to the 4th. So what slope do you get then? So the slope is 1. Now I need my y point here. So what would I need to do to get the y value? You might have to actually do it on your calculator because it's a weird one. Because I don't remember off the top of my head what the arctangent of that is. Oh, that's 45 degrees. Try it in radians and see what you get, but even what I think you're going to get in radians is not what this answer is supposed to be, I don't think. 785. Yeah, I think that might be it. Yeah, that'll work. Okay. Okay, so then when you go to find so yeah, you will need your calculator for these ones then. So when you go to do it, you would do the y minus that value is equal to your slope times x minus 1. So you're basically going to end up with, wait a second, yeah, that's right. Yeah. Y is equal to x minus 1 plus 0.785, and let's see, that would come out to be like 0.215 maybe, I think. I think that's what that comes out to be. Something around that. So basically that's all you have to do. So it adds a little bit there because you have to basically take the arctangent of that stuff. Now obviously like when you got that it was, 45, that's going to come out and tell you, I guess tangent's always going to be 1 at 45 degrees, but like 24 it'll make a little more sense I think too, like if we were to do that one. So do you feel like you need to see any more? Feel like you're good to work on some? Okay. So I'll give you some to work on, and obviously, like normal, if you have questions as you go, you can ask them. All right, let's see. Let's go 1, 5, 11, 13, 15. I'm trying to give you a little bit of a variety here, so that's why I'm giving you a few more. 19 and 25. So I'm trying to get you a little bit more of a variety there to try to get you one of each kind. If you also want oh wait, no, I did add a cotangent one. Okay, I think you should have one of each of the trig functions there. So that way you can get used to using them. I think probably what I'll do is on the quiz or test, whatever it ends up being, or both, I think I'll probably give you like a question that'll say like list the 6 inverse trig derivatives, and then that way I can check them for you and then you can use them. I should remember to actually do that. If I don't put that on there as like an actual question, you still want me to check them, I can. So you can write them all and then I'll check them for you.